Good day, everyone. Our topic for today is science, matter, energy, and systems. In this lesson, our subtopics are the following: 3.3 Energy and laws of thermodynamics and systems, inputs, flows, outputs, and feedback loops. In this lesson, we aim to discuss energy and what happens when it undergoes change, and to explain systems and how to respond to change. So now, let's discuss the laws of thermodynamics. First, we have the zeroth law of thermodynamics, and then the first law of thermodynamics. In figure 1, we can see two cups and a thermometer. In figure 1.1, a system of transforming energy. And then we have the second law of thermodynamics and the third law of thermodynamics. In figure 2, two persons hold a plate with ice above a pan with boiling water. And in figure 2.1, glass jars or mugs with internal energy. So now, let's tackle the zeroth law of thermodynamics. It comes from the word zero, zeroth law of thermodynamics, which comes before 1. So zeroth law of thermodynamics states that if two bodies are individually in equilibrium with a separate third body, then the first two bodies are also in thermal equilibrium with each other. This means that if system A is in thermal equilibrium with system C, and system B is also in thermal equilibrium with system C, systems A and B are also in thermal equilibrium. For example, consider two mugs filled with boiling water. When a thermometer is placed in mug A, it gets warmed up by the water until it reads 100 degrees Celsius. When it reads 100 degrees Celsius, we can say that the thermometer is in equilibrium with mug A. When we move the thermometer to cup B to read the temperature, it continues to read 100 degrees Celsius. The thermometer then is also in equilibrium with mug B. By keeping in mind the zeroth law of thermodynamics, we can conclude that system A and B, or mug A and B, are in equilibrium with each other. So now, let's move on to the first law of thermodynamics. The first law of thermodynamics is also known as the law of conservation of energy. States that energy can neither be created nor destroyed, but that it can be changed from one form to another. So, for example, plants convert the radiant energy of sunlight to chemical energy through photosynthesis. We eat fruits and root crops rather, and convert the chemical energy into kinetic energy while we walk, breathe, and do any household chores. So energy from the fruits are not destroyed, but rather consumed by human and it transformed into another type of energy. Then, we have the second law of thermodynamics, which states that the entropy of an isolated system always increases. Any isolated system spontaneously evolves towards thermal equilibrium, the state of maximum entropy of the system. So, for an example, above boiling water, we hold a plate with a block of ice on it. Naturally, the ice will melt. To understand this law, just visualize the ice caps and glaciers in Antarctica. If the Earth's heat continues to increase due to too much carbon emission, those ice will melt. And sadly, it is an irreversible process if we pertain to the second law of thermodynamics. The ice that melts will not freeze again. So we need to take climate change seriously. Last but not the least, we have the third law of thermodynamics, which states that the entropy of a perfect crystal at a temperature of 0 Kelvin, or absolute zero, is equal to zero. So for an example, let's visualize these three mugs with the same temperature of heat. As the temperature declines, kinetic energy will also decrease. Therefore, the entropy of the system approaches a constant temperature, approaches absolute zero. So we can see in figure 2.1 that as the temperature decreases, the entropy also decrease, or the kinetic energy decrease. And now, let's move on to our subtopic 3.4, systems, inputs, flows, outputs, and feedback loops. So, the Earth's environment consists of complex interlinked systems. Earth systems include the complex webs of relationship among species and the interactions of living organisms with the non-living objects around them. Earth systems also include cycles that shape landscapes and guide the flow of chemical elements and compounds that support life and regulate climate. So, what is a system? Excuse me. A system is a network of relationships among parts, elements, or components that interact with and influence one another through the exchange of energy, matter, or information. Systems receive inputs of energy, matter, or information, process these inputs, and produce outputs of energy, matter, or information. So let's make ecosystem as an example. So ecosystem is an example of a system in the environment. Inputs into the Earth's systems include energy, information, and matter. Energy inputs to Earth's environmental systems include solar energy as well as energy released by geothermal activity, the life processes of organisms, and human activities such as fossil fuel combustion. Information inputs can come in the form of sensory cues or genes. Inputs of matter occur when chemicals or physical materials move among systems, such as when seeds are dispersed long distances or when plants convert carbon in the air to living tissue via photosynthesis. So, for an example, as a system, the Namangan River of Mabini Negros Oriental receives inputs of fresh water, sediments, nutrients, and pollutants from the other rivers. Fisher folks harvest some of the river's system's output, matter and energy in the form of sand and gravel and fish. This output then becomes the input to the global economic system and to the digestive systems of the many people who consume fish and use sand and gravel in construction. So now, let's move on to feedback loops. Sometimes an event is both a cause or input and an effect or output in the same system, a cyclical process called feedback loop. A feedback loop can be either negative or positive. And negative feedback, uh, The output of a system moving in one direction acts as input that causes the system to move in the other direction. Input and output respond to each other's effects, canceling them out and stabilizing the system. So now, let's tackle negative feedback. Negative feedback loops stabilize systems and are common in nature. The human body's responses to heat involve a negative feedback loop. Like, for example, due to too much heat, our body reacts to it by sweating. To stabilize the body, humans seek shade, maybe under a tree, just like what we can see in our digital, or inside the comfort of their homes. So now, let's move on to positive feedback. Positive feedback loops have the opposite effect of negative feedback loops. Rather than stabilizing a system, they drive it toward an extreme. So let's tackle the positive feedback. So we can see in figure 6.1 a digital of a hill beside flowing water with lots of trees. And then in figure 6.2, we can spot the difference between the two of them. So the soil on the hill beside flowing water eroded due to the lack of trees. So this is an example of positive feedback. It drives a system towards an extreme, and it is very common in nature because once plants have been cleared from an area in soil is exposed, erosion may increase if the effects of water or wind surpass the rate of plant regrowth. And as we all know, soil erosion is due to the loss of trees in an area. That is my report is all about. Thank you so much for listening. I hope you learned something from me. And this is my midterm exam on Introduction to Graphics and Photojournalism. This output will be submitted to Dr. Sami Khayat. I'm very thankful for listening. I hope that you learned something from it. Once again, thank you very much.